Let's talk about the acoustic energy of human speech. So, the study of the sound waves produced by language. This is the acoustics. And the study of acoustics in language is referred to specifically as acoustic phonetics. And just like in articulatory phonetics, there are properties here that can be measured and looked at or heard as ways in which human sounds, those phones or their phonemes, the distinctive sounds, are distinguished from each other. And acoustic phonetics is looking at the properties of the sound waves produced from the articulation, from the production of speech. So sound waves, hopefully you know this already, are small variations in air pressure that occur very rapidly one after another. So this is similar to ripples in a pond or waves in an ocean. So if you throw a rock into a pond and you see the ripples that come out, those are waves, and sound waves are very similar, but we can't see them, but they are occurring. They're aerodynamic energy. And I'm not going to talk about why we have to look at acoustic properties when we talk about speech technology. That's covered in another video, rather than looking at articulatory phonetics, which is a bit easier to make distinctions between because I guess perhaps because we can see where the tongue is and watch it move to another part of the mouth as sounds are pronounced. But sound waves are the outcome of that. And so um, they're continuous and they're a little bit harder, I think, to make distinctions between for that reason. They're a little bit harder to map, but they're easier to work with for computers. So for that reason, we need to know what these acoustic properties of speech are. And the point of this lecture is not to know and understand every single property, but rather to become familiar with these terms and ideas, and overall to have an idea of just how complex speech is and the challenge that we're asking computers to deal with to recognize and synthesize human speech. And you're going to hear a lot of terms that you may have heard of in other classes, like from physics or um, engineering. And that's not surprising because, again, we're dealing with energy. We're dealing with aerodynamic energies. That's what sound waves are. And there's these acoustics in general have been studied in other areas as well, not just in speech. But the main acoustic properties of speech is first the speech flow, that is the rate of speaking. We can think of that in how many words per second, maybe how many um, phones or sounds per second. Some people speak very fast, like I do sometimes, and some tend to speak a little slower. And then, of course, there's the variations. When you're emotional and exciting, you tend to speak fast. And when you're sad or tired or thinking through something complicated, you tend to speak slower. So another way of thinking about speech flow is how many pauses per second, how much silence. Or in more technical terms, how much noise compared to signal, if you're familiar with those terms. Another property is loudness, also known as amplitude. So this is the amount of energy that's being produced in the sound waves, how much energy it's carrying. And this is measured in decibels. And we think of this usually just in terms of how loud. So some people speak very loud, some people speak quietly. And of course, again, when you're emotional and excited, you tend to speak louder and faster. And when you're calm, you tend to speak a little bit quieter. Or if you're tired or your voice is about to run out, that amplitude or that energy that you're exerting in your speech and producing sound waves as is less. So one thing to note about these two properties is if you look at them, they don't make distinctions, at least in English, between different meaningful sounds, right? We can say ah quietly or ah loudly. Sorry if your volume was up. But they that loudness or quietness doesn't make a difference in the meaning of a word or between two different words in English, not as far as any dialect I'm aware of. So you say you might say, well, why are we looking at these or thinking about these properties? Well, these are still properties that are coming through in the sound waves, and we're asking the computer to distinguish when are these properties meaningful and when are they not? Because which ones that change should I pay attention to and which ones should I not pay attention to? And of course, it doesn't know that these aren't necessarily more or less significant in human speech than, say, the more prominent ones, which is, for example, frequency. Frequency is one property that shows up and actually makes a significant difference in many of the subproperties of this when it comes to speech sounds. So then you have these big properties between these three that some may be significant. They may be significant in some language and not in others. So it's just as difficult to teach a computer not to pay attention or to learn to treat, sorry, not to pay attention to different properties or to treat different properties as if they weren't occurring. So loudness and softness, for example, as it is to help it and train it to make distinctions between small differences in properties that are meaningful in the language. So frequency is another property that we actually have to look at various subproperties here or different ways of looking at it. It's a very rich property, but basically frequency is how fast are the waves coming. So you can measure this by how many times per second does a trough come or a tip of the wave come, and those are referred to as cycles. One, the movement from a trough to the height of a wave down to the trough is a cycle. So how many cycles per second, or a term for that measurement, cycles per second, is hertz, and sometimes thousands of cycles per second. So here you might hear kilohertz. Frequency, the difference in frequency makes a difference in pitch in speech. How fast waves is high pitch and slower waves are low pitch. And this is less significant in English, but in tonal languages, this is very significant. It can make the difference between two words. Uh, it can make the difference in English across an utterance, a rise and fall in pitch, not over a word, but over a whole speech segment or utterance or sentence, can make the difference in meaning, because sometimes we don't bother to change the grammar, for example, between a question and a statement, and just say it as a statement. You eat yet? Which sounds like a statement instead of saying, did you eat yet? And the only real difference between you eat yet and you eat yet, so between the statement and the question, is that the question ends up on a higher pitch at the end. Then another thing that is a feature here, part of frequency, is the fundamental frequency. So speech sounds don't just have one single pitch being stimulated as we speak. We have multiple frequencies going on. So it's complex sound, like a harmony that we produce as we speak. The fundamental frequency then is the average of those frequencies at waves that are occurring at the same time. So these are all acoustic properties, and you might notice that there's fewer properties. There's really only three main ones. There are some different ways of looking at the frequency and measuring it. But really overall, there's three properties here compared to the at least six properties that we looked at in articulatory phonetics. So looking at something complex with fewer measurements makes things a little bit harder. Now, all of this you can talk about and use words. You can measure these things. Actually, you could think about this in terms of if you went to the ocean and you wanted to know about the weather and the rain and the wind and the temperature, perhaps, but all you could do was measure the waves coming from the ocean. That's the only thing you're able to set up to measure. And from that, you're going to have to tell all this other information, which would be pretty informative. Waves, are dependent on a lot of those factors. What you could do is put in, say, a metal plate at the beach or somewhere in the middle of the ocean and steady it on the hard ground somewhere, anchor it down, and then connect, say, uh, a wire to measure how much well, you could measure different things, right? So you could make it so it would vibrate. So every time a wave hits it, it would vibrate a little bit, and that would be able to measure that energy, right? The amplitude. If it's moving a lot, there's a lot of energy. If it's moving just a little bit, then it's less energy. It's not hitting the wave as hitting that metal plate as much. And by the way, this is exactly how a microphone works. It does that vibration. It's connected to electrical wire, and it's measuring these things in sound waves. But if you think about in the ocean, that would tell you, okay, we got big, really hard waves. Probably it's stormy, right? You could um, set it up so you could tell when the highest point of the wave comes. And then you could measure how high those waves are, which would also probably tell you something about energy and would tell you how fast the waves are coming. So it would be frequency. And that could also tell you something about other things in the environment. But you're kind of stuck to these few properties to be able to interpret other things. And that's similar to how we're kind of stuck with recording a microphone and the measure of sound waves to tell us about the details of what's going on in a human mouth. Now, we could just talk in terms of hearing. It's a little bit easier, I think, to look at it. So there are these tools that will turn this measurement of that metal plate, that vibrating metal plate in the microphone into something we can see. So this is called an oscillogram, also just known as a waveform, and it's kind of trying to interpret those sound waves as something visual. And this is the waveform for the word phonetician. You can see here the IPA symbols for phonetician, which is phonetician is a person who studies speech sounds. And you can see how the sound waves change from uh, small, not a lot of um, energy, perhaps, not very loud, but very, very intense. So probably very close together, high frequency versus the O, which seems much louder, but perhaps it's hard to tell from this waveform actually, perhaps lower frequency. And you can see how it changes through the sound. You can see some similarities here with the sh, which is the friction. It's highly constricted but not stopped, and the F, which is also highly constricted and not voiced. So there's no vocal cords engaged in either of these sounds compared to the vowels, which are louder, which do have the vocal cords and have a much more open mouth. So you can tell some differences between sounds, or maybe not you and not me, but a phonetician could make a lot of sense out of this waveform, but not as much distinctions or as much information as is actually needed. And so for that, there's another way of viewing sound waves, which is called the spectrogram. And this is looking just at the frequencies. So this is just the frequencies, the hertz or the cycles per second that are engaged with these sounds. So it's the same sounds. So you can see the F is darker up here in the higher frequencies. The O is darker down here in the lower frequencies. One thing you can note really quickly here, if you're looking between the vowels and the consonants, is that a lot of these consonants just kind of have this vague, fuzzy, all across whatever frequencies they cover, whereas the vowels have these distinct black bands that go. You can see, and they're in different places. So this is how vowels are distinguished on the spectrogram. Vowels behave in an interesting way. The N is not quite there, it's almost there, and that's because the N is very vowel-like, because there's not a lot of constriction of the air as it goes through the nasal cavity. And you can see as the person finishes the word, it kind of gets a little quiet here. So this is where you can measure the frequencies, the most intense frequencies that will tell you about different sounds and speech sounds. And so again, an expert could tell a lot more about this than I can just by eyeballing it. But it gives you an idea of how, again, how complex. Just for example, that we're engaging multiple frequencies, not just one for all of these sounds, and how we do how different frequencies are stimulated for different sounds. For computer, of course, all of this is represented as numbers, but we can see it here and eyeball it, and it looks visual, even though it's all about speech, which is more convenient. The only other thing that we mentioned that we don't see here, but I can show you on the next slide, is to take that same word phonetician, and this is the fundamental frequency. So this is taking that that oscillogram, that frequency map, as it were, and just mapping not all of the frequencies, but the average frequency for these sounds. And you can also see how it changes over time, over the word and over the vowel. So you can see how you could maybe map um, the same phones here in, say, Mandarin Chinese and compare the relative fundamental frequency to be able to tell how the tones work in a language that's tonal and pitch over how pitch changes over a sentence if you wanted to study intonation. So this is a lot of stuff. This has to do with physics, has to do with sound waves, aerodynamic energy, how we measure it. It has to do with audio signaling, processing, acoustic engineering. All of this comes into play. The big idea here is there's a lot of things going on. There's a lot of small differences, as you can see in these spectrograms and waveform. And this is a challenge. This is a challenge for a relatively simple and dumb machine like the computer to be able to first make the distinctions that need to be made between, say, an O and an S sound, and an S sound and an I sound, which are some of the easier ones because you have these clear formats here called formats, the dark bands, um, that are meaningful differences in English, but then not to make those distinctions and transcribe a different letter, for example, if it's not a meaningful difference in another language, or if you have someone speaking a foreign with a foreign accent who's making distinctions that wouldn't be made by the average English speaker. So being able to both make in all of this mess, the distinctions that need to be made and then being able to kind of collapse or ignore the distinctions, for example, in English, whether or not that don't need to be made. So, for example, in English, the fundamental frequency, the average frequency differences, say, between the average frequency of a woman, which is going to be higher, than men, which is going to be lower. And by the way, it was a huge advancement in speech technology to be able to go from a program that was able, first of all, to do a transcription from the audio, but then you had this another huge step to go from, okay, we're trained on one voice, and then a huge step from one voice to multiple men's voices or women's voices, and then be able to handle the same uh, language with the same words when there was a mixture of women's voices and men's voices with different fundamental frequencies. So it was actually quite a step in advancement to be able to get to that point. So these are hard. These are complex things, and this is quite a challenge for the computer to handle.